Hey guys, so today we're going to do an induction problem. So first off, I'm going to start with like a mini lecture on induction. So it's basically proving this proposition right here true for every n value, and n value should belong in natural numbers. So it can be 1, 2, 3, like the natural number, and then to prove that if the proposition takes in that n value, it should be true. So there are three steps to one induction problem: base case, induction hypothesis, and relative step. Base case is proving P of the proposition for the simplest case that is. Usually it is going to be P0, P1, or it depends on the problem. So it's not a hard and fast rule that it's going to be 0 and 1, but usually it is 0 and 1. Then inductive hypothesis is just like writing on the statement, which is like assume that for some k is greater than 0, pk is true. Now this is just an assumption that we're making. The inductive step is where the actual proving happens, which is basically given that pk is true. This is our inductive hypothesis. We have to prove that pk is true. pk plus 1 is true, my bad. And this would basically then prove that pn is true for all n in natural numbers. Question problem. This is the first problem in the worksheet. It's basically asking us to prove the sum of the first odd numbers in n squared. N here is the index, not the value itself, not the odd number itself. So make sure you remember that. Our smallest case will be k is equal to 1. So n, the index, is 1. What are the odd numbers? 1, 3, stuff. So what is the first odd number we have? 1 is equal to k squared, so 1 squared. So there, we proved it. This is true. We do inductive hypothesis next, which is basically just rewriting the problem statement as well. So assume first k odd numbers. Assume that assume that for some k greater than 0, the sum of first k odd numbers, which is 1 plus 3 plus dash dash dash, k minus 1, again, k is the index here, not the value itself, is k squared. This is our hypothesis. It's really necessary to understand what we're inducting on. We're inducting on the index here, not the number itself. That's why it's not 1 plus 3 plus dash 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 k is equal to k squared. It's the kth value. Now for inductive step, remember that we have to do k plus 1. So we have to prove the proposition for k plus 1. So this is the proposition for k. So what is it going to be for k plus 1? So we add the k plus 1th term. So we do 1 plus 3 2k plus 1 term. 2k minus 1 plus 2k plus 1. So this is the k plus 1th term. This is the kth term. Taking a look from the hypothesis, we know that this value is k squared. So this basically becomes k squared plus 2k plus 1. We know that this value is k plus 1 whole squared. And that, how do we know this? We have a formula in math. A plus b whole squared is equal to a squared plus b squared plus 2ab. Okay, we just put that in. So we proved this for k plus 1. And that is where inductive step is over. Why does this work? So the first thing we did was base case, right? Proved it for k is equal to 1. Let's see what we are doing in the next step. We're proving it for some k plus 1, right? Now let's say k is equal to 1. We prove that it should work for k plus 1, right? So it should work for. Now, if you apply the inductive step again, it should work for this as well. And we keep going till n, like any arbitrary n, as long as it belongs in natural numbers, because there is no like terminating condition. So this is why induction works. I hope it helps. Thank you for watching.